Hi folks, welcome back to the third video in the 10.5 Polar Coordinates video lecture series. So in this part, we're going to take a look at some graphs of polar equations, and I've picked ones that are pretty common, but also structured in a way that we can hopefully see the patterns and recognize, okay, if the equation looks like this, then the graph is going to look like this. So for the first category, I picked lines. So what that means is that you can graph a line in polar coordinates, and it's going to be through the origin, or it could be horizontal, or it could be vertical. All right, so let's do a couple examples. So for example, if I have theta equals pi over 3, then what that's going to look like on my graph is just a line through the angle pi over 3, okay? And it's going to go through the origin, but that's basically what a graph of that looks like. So if you ever see theta equals just an angle, it's going to be a line going through the origin. Now you can get fancy and you can draw horizontal lines and vertical lines. So for example, if you had an equation like this, r equals 2 cosecant theta, all right, what that would look like on your graph would be a horizontal line crossing at 2, kind of like this, okay? Now, if you change your trig function and you say r equals 2 secant theta, what you're going to end up with is not a horizontal line, but a vertical line. And so it's going to touch right here at the edge of that second circle, and it would be going straight up and down. All right, so when you see equations of those types, theta equals a number, r equals a cosecant theta, or r equals a secant theta, you're going to get some sort of line. The next common type of polar graph is a circle. So we've actually already seen some of these in the work we've done in the previous videos. So let's say you had r equals 2, okay? What that would mean is that on your graph, you have a circle centered at the origin with a radius of 2. So we would get this very circle right here, okay? So r equals 2 would give you a center with the radius of that number centered at the origin. Now, if you wanted circles that were off-center, so either to the right or left of this origin or above or below the origin, then we have equations of this type. So if I have r equals 3 sine theta, okay? So if I have r equals 3 sine theta, then what I'm going to have is a circle that is above and will have a diameter of 3. Okay, so this number right here is the diameter in this case. So I'm going to start here. I'm going to count up to 3. And when I draw a circle with a radius of 3, that will be what that picture looks like. Now, if I had a negative 3, then this picture would just be below that horizontal axis. Now, you could also have a circle that has shifted to the right or the left. So let's say you had r equals 4 cosine theta. This would mean that I have a diameter of 4, and I'm shifting my circle to the right of my origin. And I'll draw a circle. And that's what that graph will look like, okay? So a few important things here. When it's centered at the origin, this is the radius, the number is the radius. However, when it's up or down or side to side, that number is the diameter, not the radius. All right. Let's take a look at Archimedes' spiral. I think this one's a pretty neat one to look at. But when you have an equation that's just r equals theta, what you end up with is a pretty cool spiral that kind of goes around like this, all right? And if you change numbers in front of theta, you can get different sized spirals. So feel free to play around on Desmos. You could see like r equals a theta, and if you change a, you can see what happens to the spirals. Or you could think what happens if you have like a negative theta. That's pretty cool to look at too. Okay, so you can look at that on Desmos on your own time. All right, let's take a look at, we're going to skip down to the Lemniscat, all right? So the Lemniscats are the last type of graph that we'll take a look at in this section. And the Lemniscats have also a very specific formula. So these are the only ones that have r squared equals something. So it's not r equals, but it's r squared. And so what we have here is we have a bow tie looking situation, okay? So if I had, let's say, r squared equals 4 sine 2 theta, and I graph that, what I'm going to get is a diagonal bow tie that goes through the center and has a bow tie length of 2 on one way and then a bow tie length of 2 in the other direction. And I know that because the diagonal ones have the sign there, okay? So A equals your bow tie length, but like only one part of the bow tie, not the whole thing. Now, if you type in, you make one small change to your equation, you type in r squared equals 4 cosine 2 theta, okay? So we're not talking about sine 2 theta anymore, we're talking about cosine 2 theta. What happens is A will still be the bow tie length, so one end of the bow tie is 2 units away from the center, but this time your bow tie is going to go horizontally, okay? Kind of looks like an infinity symbol. But again, it's not this number, but it's the square root of that number that tells you your bow tie length, okay? So take some time, play around Desmos, and see if you can figure out some fun, cool patterns with these. But polar coordinates definitely come up again when you get to Calc 2, and it's going to be really important that you know how to visualize these. All right, so we're going to stop here for the third video. Come on back for the last video where we look at 2 other important and common shapes for polar graphs. All right, see you there.